So the standards that we've already seen up until this point is we've gone through the standard by playing the stack it game of figuring out how to classify the structures for finite abelian groups of a given order, right? If I tell you you have 246 elements with which to build an abelian group with, then you can give me now a list of all possible abelian group structures that you can make with that set of elements, right? Just by taking the prime factorization of that order and then stacking up the chips. Right? So that was standard number 11. But that's a big theorem, and there's a lot of ingredients that go into that theorem, and the rest of our material for this semester are about those ingredients. So we talked about one ingredient already in standard 8, which is how do we actually build up smaller groups into bigger groups. Like, that's the operation of the direct product that we talked about. The most important ingredient in the direct product being the least common multiple theorem, right? The LCM theorem that was the main ingredient in number 8. So that gave us a way to build up bigger groups from smaller groups. And the picture, actually, let me go back to this picture for a second. The picture that emerges is that if you give me, rewind this a little bit. If you give me two completely unrelated groups, like a group here and a group here, I can use the direct product that we've already talked about to assemble those groups into a bigger group whose elements are ordered pairs. Right? So that's a building operation. But in order to get where we're going with this theorem, we also need to know how to do the opposite, how to take a group and break it apart into pieces that would go back together using a direct product to give me the original group. So how do I also break a group apart? And that's what Standard 7 is chiefly about. Standard 7 that we're going to talk about today is about dividing the structure of a group up to discover its constituent pieces. So my example when we first introduced this is if we take a group like D5, okay, not an abelian group, so it's not going to be a part of the main theorem for the course, right? But it's a group of symmetries of a pentagon. It's got 10 elements, 5 times 2. And initially, these 10 elements are just sort of a bucket of undifferentiated group elements. But what we want to do, and this is the theme of today, is to bring organization to the elements in that group by thinking first about subgroups. So for example, the cyclic subgroup generated by the rotation by 72 degrees of the pentagon. That cyclic subgroup consists of these 5 elements, right? The 4 powers of R, and then the 5th power of R, which would be the identity. There's also another subgroup that would be just the identity element and the, what would we call this, the reflection of the pentagon, E and T. That's a subgroup as well. It's got 2 elements in it. And this group happens to form its own little, what we call an internal times table, right? That all the rest of the elements can be found by multiplying one of these by one of these. TR, TR squared, TR cubed, TR to the 4th. Right? And so this helps me to see why it is that there's a nicer internal sort of substructure that makes up D5. That I've got one subgroup over here that's on this first row, another subgroup over here that's on this first column, and everything else in my group is a product of something from this group, from something from this group. Something purple times something green. Right? Can account for every element of D5. So here's a question to get us started. What group that we know by another name would this subgroup E comma T be isomorphic to? What is that subgroup E comma T the same as? What group do we know that has 2 elements in it? Z2. Z2. So this first row right here looks like just a copy of the additive group mod 2, right? With the identity playing the role of my 0 and the T playing the role of my 1. And if I take 1 plus 1, I get 0, mod 2. Because T composed with T gives me identity in D5. Right? So this subgroup looks like Z mod 2. It's the same as. It's isomorphic to Z mod 2. What about the cyclic subgroup generated by R? What group is it isomorphic to? Z5. Z5. How do I know it's cyclic? What would be a generator for this subgroup? R is a generator for this subgroup, yeah. In fact, R squared is also a generator. R cubed would also be a generator. R to the 4th would also be a generator. It's got 4 generators because the Euler phi function of 5 is equal to 4, right? So yeah, it's cyclic. It's got 4 different choices of a generator that I could have. So as a cyclic group of order 5, it's isomorphic to Z5. Right? So there should be a way in which we can say that D5 is built out of a Z5 and a Z2 producted together. But what's the problem with that viewpoint? If I just take Z5, direct product Z2, that's going to be a group that has how many elements in it? 10 elements. Order of this one multiplied by order of that one. But what else could I know for sure about this group?
It has an element of order 5 and an element of order 2.
It's got an element of order 5, so that could be our R. It's got an element of order 2, that could be my T. What else is true about this finite group? Casey?
It's cyclic?
It's, well, it has two cyclic factors, right? Z5 is cyclic, Z2 is cyclic. Oh, is it cyclic? I'm going to backpedal on that.
Okay.
Well, is it cyclic? If we're playing stack it with this group. I've got a green chip and a red chip. What can I do? I can stack them together. To what group is Z5 plus Z2 therefore isomorphic? Z10, because 5 and 2 are relatively prime. We can do that. That's the LCM theorem, right? So I double clutched on it, but Casey is right. This is a cyclic group, in fact, of order 10. So what does that tell me about whether D5 is actually isomorphic to this direct product? Why not?
D5 isn't cyclic?
D5 is not cyclic. How do I know D5 is not cyclic?
Doesn't have a generator. Like, it doesn't have anything of order.
It doesn't have anything of order 10.
There's no one element that will get both R's and T's.
There's no one element that can generate both R's and T's. My other favorite reason for this, that I've encouraged a lot of people on quiz 6 to use more, no, quiz 11, is what also do we know about every cyclic group? Every cyclic group has to be abelian. What about D5? D5 is not abelian, therefore not cyclic. Right. So for sure, D5 is not an external direct product of Z5 with Z2. Because the external direct product of Z5 with Z2 is the cyclic, and in particular abelian group, Z10. Right? And it's not the same as Z10. There's no element of order 10 here. It's not abelian. So these groups cannot, in fact, be the same. Okay? So that would seem to be kind of a problem. But let's try and get as much out of this correspondence as we can. So here's the theorem that we'd like to prove. And this is going to be the centerpiece theorem for the week. It's called Lagrange's theorem. And it's probably one of the most important structure theorems in all of the theory of finite groups. So Lagrange's theorem says that if the order of a group is equal to n, and H is a subgroup of G, then the order of H is a divisor of n. So Lagrange's theorem says for any group at all, any finite group at all, any one of its subgroups can only have a number of elements which is a divisor of the order of the whole group. Right? If you give me a group of order 15, I cannot find a subgroup of that group of order 4 or of order 9. But I may be able to find a subgroup of order 3 or order 5. Right? So the only possible orders for subgroups are divisors of the order of the big group. That's Lagrange's theorem. Do not use Lagrange's theorem backwards. Right? Just because there may be a subgroup of a given order does not guarantee that there is a subgroup of a given order. Pay attention to the if-then. The existence of this subgroup is already a part of the if in Lagrange's theorem. So we already know that there's a subgroup. Then Lagrange's theorem says that subgroup has to have an order that divides the order of the group. It doesn't go backwards. If you give me the order, I can't necessarily produce the subgroup. Right? But if you give me the subgroup, I know the order has to divide the order of the whole group. So the question is, how are we going to prove this? I'm hoping that over the next class or so that we collaborate together to prove this theorem. And the way we prove it, I like this picture over here, because this theorem, the technique relies on us taking the elements of this group and organizing them into a row-by-column table, right, which is what I did with D5 up here. 5 columns, 2 rows. And that 5 and that 2, if we're able to do this, right, that 5 and that 2, those are both divisors of 10. Right? And so that divisibility is going to come from our organization of the elements of this group into this nice row-by-column table. So there's all 12 elements of A4. And so the question that I'm kind of trying to pose here is, how do we bring some order into this chaos? Right? What subgroup of A4, or maybe subgroups of A4, best explain its structure? The goal of today is going to be to take A4 and figure out what are some different ways of arranging the elements of A4 into a row by column kind of scheme. One way to do it would just be to take all the elements, all 12 of them, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, whatever. We could arrange all 12 of the elements of A4 in just one big long row. Not very illuminating, but certainly A4 is a subgroup of itself, right? Every group is a subgroup of itself. We could also, if we wanted to, arrange them into one big long column. What do you think the first element in this column would be?
Identity.
Yeah, I would just put the identity as the first element here. And the identity element, as a set containing just that one element, that's also a subgroup of A4, right? So we kind of are starting with these two different subgroups that every group has, right? Take my subgroup here to be equal to the whole group, or take my subgroup to be just the trivial subgroup. But neither one of those would seem to illuminate the structure of this group very much. So what we'd like to do is we'd like to see if there is a different way to arrange rows by columns. And given that the order of my group here is 12, what are some options for what the dimensions of my little array could be here? 3 by 4 is an example. So if I can somehow arrange the elements into 3 rows and 4 columns, or vice versa, I'm going to kind of draw it as though it's 3 rows and 4 columns. Right. This would require me, if I'm going to do this, I need to find a subgroup that has 4 elements in it. So maybe there's one option. So maybe we can find a subgroup of 4 elements with which to do this. Or what's another way? We could try 6 by 2. So find a subgroup that has 4 elements. I could try looking for a subgroup that has 6 elements in it. And there's maybe a couple more. What about 2 by 6? Right, a subgroup that has 2 elements in it, and then we end up having 6 rows in this table. Or there's one more possibility I don't have up here yet, and that's instead of 3 rows, we do 3 columns and 4 rows. Right, so any one of these would seem to be a viable way of figuring out the structure by using a subgroup. Find me a 2-element subgroup, find me a 3-element subgroup. Now pay attention, Lagrange's theorem does not tell us whether any of these actually exist. It only tells me that if a subgroup does exist, it's got to make one of these tables for me. Right? That's what the theorem would say. That any subgroup of A4 has to have order 1, possibly order 2, or possibly order 3, or possibly order 4, or possibly order 6, or possibly order 12. That's what Lagrange's theorem guarantees. Not much. Right? But I want to use this as a way for us to think about the structure that's going to permit us to prove this theorem. So the Scratch app that I provide for you, that I'll have you get started with in a minute here, actually starts out by giving us a 3-element subgroup of A4. And that's done just by taking one of the 3 cycles and forming the cyclic subgroup that's generated by that 3 cycle. I think the one in the app might be 1, 2, 3. I think so. It's these first 3 elements that form a cyclic subgroup. So the only difference between the visual we had on the screen a minute ago and what this app is showing me is that it's showing the subgroup in a column instead of a row. So if you're going to square it with your notes, just make this the rows and those the columns rather than the other way around. What this app permits us to do is to take this subgroup, the elements of this subgroup, and multiply all those elements of this subgroup by another element, either on the left or on the right, because that matters in A4, which is not an abelian group, right? For example, if I were to multiply every element of H by, I don't know, the 3-cycle 2, 3, 4, if I want to multiply all these on the left by 2, 3, 4, then I'm going to get a set that now has these 3 elements in it. 2, 3, 4 times identity, 2, 3, 4 times 1, 2, 3, 2, 3, 4 times 1, 3, 2. And this app does that computation for you to simplify those products of permutations to show you what are the three elements that belong to this, what we call a left coset. Right? So what is happening here, to correlate it to the model that I'm kind of putting down on the other screen here, is that we're starting with a subgroup of A4 that consists of the identity, it consists of 1, 2, 3, and it consists of 1, 3, 2. Right? And that's a subgroup. It's a subgroup of order 3. But what I'm asking you right now is, what do you notice about this left coset? So the left coset is what I got by multiplying all these elements on the left by 2, 3, 4. And I get a set that has these elements in it. What do you notice about that set?
They're all different elements than we started with.
They're all different elements than we started with, right? So none of identity 1, 2, 3 or 1, 3, 2 are present in this coset. So I could make this coset a new row in my table, right? Just by multiplying this identity by 2, 3, 4, here's where I think the ordering is kind of convenient to keep in mind. By multiplying the identity by 2, 3, 4, I got 2, 3, 4. And so I'm going to put that one under the identity here, so 2, 3, 4. By multiplying 2, 3, 4 by 1, 2, 3, I got 1, 3 composed with 2, 4, I believe. Yeah, I get this one, right? So this times that is going to give me 1, 3, 2, 4. So I'm going to write that here, 1, 3, 2, 4. And then by multiplying 2, 3, 4, 1, 3, 2, I got 1, 4, 2. And none of those elements were any of the ones that we started with in our subgroup. So I'm going to kind of keep a list of these observations. That the left coset was disjoint. Left coset 2, 3, 4, H was disjoint. Okay, what else do you notice? So our original first row here was a subgroup. This new row, this green row, is not a subgroup. How can we tell? It doesn't have the identity. So even before checking any of the other properties, we know for sure that this is not a subgroup. 2, 3, 4, H is not a subgroup of G, A4. Okay, what else? What about how many elements are in this left coset? This is something you might not be surprised with initially, but I want us to be surprised by it. How many elements are in this coset? There's 3. That's kind of important. 2, 3, 4, H has 3 elements. So why is this a surprise? Or maybe why is this not a surprise? How do we know that in the process of multiplying all of these 3 different elements of my subgroup by the same 2, 3, 4, how do I know that 2 of these might not end up going to the same element? Right? How do I know that the correspondence between the elements of H and the elements of this left coset is 1 to 1? Let me ask you this. How could we go backwards? If I wanted to go backwards from the elements of this row to the elements of my original subgroup, what could I do?
Multiply by 2, 3, 4's inverse.
I could multiply by the inverse of 2, 3, 4, right? And because this assignment has an inverse, what do we know about the function which takes me from H to this left coset? If it's got an inverse function, it must be, well, the composition of the two will be the identity. But what do we know about the function? Any function which is invertible must be what kind of function? Yeah, in order to be an invertible function, it's got to be 1 to 1. And if it's 1 to 1, that means that 2 different elements cannot go to the same place, right? And vice versa, because the inverse has to be able to return each of those elements from exactly where it came from, right? And so this assignment, what we can say is that H is bijective with its left coset, 2, 3, 4, H. And that should be true for any coset that we make, right? we can always go both ways. Whatever element I multiply by to get me to a coset, I can multiply by the inverse of that element to get me back to the original subgroup. And so this tells me that every left coset of H, regardless which one I choose, is going to have how many elements in it? 3. And so each row of my table is going to have 3 elements in it. And going back to Ashley's observation that the coset was actually disjoint with the original subgroup, do we believe that these other cosets will be disjoint to the others as well, so that each element of this is only going to appear in one row, one and only one row? We should try to convince ourselves of that also. Maybe I'll make some space on the screen. We'll just do a quick proof. How do we know? How do we know that we can't have an element belong to 2 different cosets? So if I have an element A that belongs to both a coset GH, and it also belongs to, let's say G1H, and also belongs to G2H, then what is this going to mean? Right. If I have an element that belongs to 2 different cosets, G1H and G2H. First of all, and this is probably the most important thing about doing proofs with cosets, and doing proofs with cosets is probably the most challenging thing we're doing now for the rest of the semester. Okay, this is Standard 7. Is just unpacking the definition of left coset. So in English, I would read this. A is an element of the left coset of H by the element G1. And by definition, G1H is the set of all elements that can be written as G1H, where H is an element of the subgroup, capital H. Right? So to say that A is an element of this left coset means that there exists some little h in the subgroup H, such that A is equal to G1 times H. And for the left coset G2H, it's the same story. And since it's a new element of the subgroup, I should probably call these H1 and H2. There exists an H2 belonging to H such that A equals G2H. Right? And so what I get here is if A belongs to 2 different cosets, then A must satisfy these 2 different equations. Right? A must be a multiple of G1 by an element of H, and it must be a multiple of G2 by an element of H. Whoops, and I forgot my subscripts on those H's. H1 and H2. Right? So to belong to this left coset means to be equal to G1 times some element of the subgroup. To belong to this coset means to be equal to G2 times some possibly other element of this subgroup. And so what I want to do here is see what this combination of 2 equations can tell me about A, if anything. Well, since both of these are equal to A, we can set them equal to each other by the transitive property of equality. Right? So this is going to tell me that G1H1 equals G2H2. And this sounds almost like a chemistry equation, like stoichiometry. C1V1 equals C2V2. Whatever. G1H1 equals G2H2. And actually, what I'm going to do with this is I'm going to try to get the G's all onto one side of the equation and the H's all onto the other side. And I could do that in one of 2 different ways. I'm going to choose to multiply by G1 inverse on the left of both of these equations. Right, we can do that. G1 inverse multiplying on the left of both of these. And the new equation that I get is going to be just H1 is equal to, color coding this starts to get labor intensive, but it's worth it, I promise. G1 inverse times G2 times H2. Okay, and now I want to get this H from the right side over to the left side, so what do? Multiply by H2 inverse on which side? The right. H2 inverse. That's going to cancel out my H2 on the right side. And so what I find out is that G1 inverse G2 is equal to h1 times h2 inverse. And that seems like it's meaningless, but I promise it is meaningful for this reason. What do I know about h1, h2 inverse? Where does it live? Yeah, and so h1 lived in h. h2 lived in h. So where does h2 inverse live? Because
Well, it's a group.
H is a subgroup, and so the inverse property says h2 inverse has to live in H. And then where does h1 times h2 inverse live? Because closure property for subgroups. Exactly, right. So the meaning of this last equation here, why it matters, is that we've now shown that if A belongs to two different quote-unquote cosets, G1H, G2H, then they can't be that different from one another. In particular, G1 inverse times G2 has to be an element of H. So, in fact, what we can use this to do is we can use this to define an equivalence relation. And we can actually define left cosets using this equivalence relation to say that two elements belong to the same coset. I got to get some more space. Maybe I'll write it bottom left over here. X and Y belong to the same row, right? The same coset. Left coset of H, if and only if X inverse Y belongs to H. And this definition down here, we can check, defines an equivalence relation on the elements of H. And anytime we have an equivalence relation, the equivalence classes of that equivalence relation define a partition of the set on which it's an equivalence relation. And because it's a partition, that means that every element is going to be in one and only one equivalence class. So every element of my group belongs to one and only one left coset of a given subgroup. And the assignment of subgroup to coset is a one-to-one correspondence. So every coset has the same number of elements as the subgroup did. And so what does all of this mean? It means that we can divide up, once I fix a subgroup, then every coset of this subgroup is going to have the same number of elements as the subgroup did. So every row of this table is going to have the same number of entries as the first row. And also that every element in my group is going to appear exactly once in this table. And so that accomplishes this organization of the elements of this group into a row by column chart, where the first row is my subgroup and each successive row is a coset. Can be a left coset, can be a right coset. For the right cosets we get a slightly different equivalence relation, but the same idea still works. 2, 3, 4H gives me that second row. Let's quickly jump back to the app for a second and see if we can find a different row. So going back to my original subgroup. So 2, 3, 4 gave us the row that we just looked at. Let me ask this question real quickly. What would be another example of a left coset that's going to give me the same three elements, do you think? Besides 2, 3, 4H. What else could I use as my left coset to give me these same three? 2, 3, 4 is inverse? Let's try it. So 2, 3, 4's inverse is 2, 4, 3. There's the left coset of 2, 3, 4. 2, 4, 3 rather. So that gives me something different. So the inverse of 2, 3, 4 does not in fact give me the same coset as 2, 3, 4 did. So coming back to the app for a second. Again, here is my original coset of 2, 3, 4. Here's a question. If I want to make sure that 1, 4, 2 belongs in my coset, how can I realize 1, 4, 2 as a multiple of something times one of these elements? What's the low-hanging fruit here? Identity. What can I multiply the identity by to get 1, 4, 2? How about 1, 4, 2? That does it. So 1, 4, 2 times H gives me the same left coset as 2, 3, 4 times H. What other left coset do you think is going to give me the same three elements? How about 1, 3, 2, 4? Yeah. It does, right? So any three elements in this example that belong to the same coset, any one of those three elements is capable of representing that whole coset. This is actually the magic that's going to get us into Friday, because when elements are arranged into cosets just so, right, those elements can stand in for their entire row, and the properties of that entire row can be determined by the properties of that element. Right? That's the magic, right? So 2, 3, 4H is the same as 1, 4, 2H, is the same as 1, 3, 2, 4H. 2, 4, 3H would be the same as 1, 4, 3H, would be the same as 1, 2, 3, 4 times H. How do you think I'm going to get this last row? Yeah, multiply by any element that doesn't already exist in my chart. Right? We know that since the cosets are disjoint, that remaining element has got to be a part of this last coset. But then, because any element in that coset can represent that coset, any of my three missing remaining elements can be a representative for this last row. So what would be an example?
1423.
1423, that 2 plus 2 cycle. Let's try it. 1423. Yep, that exactly accounts for the remaining three elements. So let's make that the representative for my last row. Get back to my table here. So 1423, 1, 4, 2, 3, 2, 3H. And so this entry here would be 1, 4, 2, 3. And then the other two missing elements were 1, 2, 4, and 1, 3, 4. Great. Okay. So Lagrange's theorem tells me that if we can prove all of these statements that we're speculating are true about cosets, right, namely that all the cosets are disjoint from one another, right, so I can't have an element belong to more than one different coset, and that all the cosets have the same number of elements as one another, then that means that any finite group can be arranged into one of these row by column tables where the first row is a subgroup and the remaining rows are the cosets, either left cosets or right cosets of that subgroup. And if that's true, that forces the number of elements in this first row to be a divisor of the total number of elements in the group, right? Because I started with 12 elements, and I can arrange it into a 3 by 4 table where the first row is a subgroup. That must mean that that first row has a number of elements that divides 12. Right? So that's the shape of the proof of Lagrange's theorem.